Yes. Okay. Yeah. Sorry for all the delays and the problems. PhD in astronomy, and I still can't work a laptop. I think that says a lot, doesn't it? So if we go to the next slide, I just thought I'd explain who I am. So I gained my PhD in astrophysics from Cardiff University a year ago this month, actually. Yeah. And during my PhD, I studied the infrared universe and also a simulated universe created using supercomputers. And I was looking at how the stuff between the stars, so the gas and the dust between the stars, changes over cosmic history. But while I was doing my PhD, I kind of realized that my true passion was talking about other people's science rather than actually doing the science myself. And so now I work for an app called Skyguide, which is part of Fifth Star Labs. Unfortunately, it's only available on Apple at the minute. This is a request that we get all the time, and never say never, but yeah, on Apple at the minute. That's kind of my day job. So, you know, I write articles and I keep the app functioning and, you know, do all sorts of stuff. And I also dabble in a bit of BBC radio and TV. So, you know, whenever there's an interesting space story, I'll get a phone call and I'll go and do that. And yeah, it's all good fun. And then aside from kind of obsessing over space, I like to cross stitch. That's my hobby. And I'm also owned by a cat because I think anyone who has a cat knows that you don't own them, they own you. So if we go to the next slide, please. So in this lecture, we're going to do a big overview of the James Webb Space Telescope project as a whole. We're going to explore why it's an infrared space telescope as opposed to one that studies the universe using light that we can see with our eyes. We'll have a look at that fascinating deployment sequence because, of course, it is like one of the most complex, if not the most complex space telescopes that's ever been launched. We'll explore the instruments that are on board, and then we'll finish off with a look at what it's going to do in its first year of science, because, of course, that's already been decided. Next slide, please. Okay, so JWST, the James Webb Space Telescope, it is the next big flagship telescope. Quite often it's attributed just to NASA, so the American Space Agency, but actually it is a collaboration between NASA, ESA, the European Space Agency, and CSA, which is the Canadian Space Agency. And it's named after someone called James Webb, no surprises there. And that he was the NASA administrator between 1961 and 1968. He's sometimes referred to as the father of Apollo because, of course, he was administrator during that critical development time for the Apollo missions and the launch of the early ones. Now, something really important to know about the James Webb Space Telescope is that it is not Hubble's replacement. And this is a phrase that is sometimes used in the media. It's actually Hubble's successor because it is designed to work alongside Hubble. And, you know, we've managed to get to the point where it will actually work alongside Hubble because, you know, 30 years old, the Hubble telescope, it was getting a bit touch and go whether those two would ever actually operate together. But as Hubble's successor, part of its mission is to peer deeper than ever before. And to do that, it needs to operate in the infrared. And we'll see why in a little bit. And apart from staring deeper into space than ever before and seeing the light from the very first stars and galaxies, its other kind of priority is to characterize the atmospheres of potentially habitable exoplanets. So we're sort of out really of the era of mass discovery of exoplanets. Of course, that's still going to be ongoing, but we're now entering this new era where we've got loads and loads of exoplanets, and now we really want to try and understand these worlds, especially the worlds which are close to us, because, you know, when the Earth goes on fire, eventually, we need somewhere to go, right? Next slide, please. Okay, so I think probably the most recognizable and iconic feature of the James Webb Space Telescope is its unique origami-style folded design. And that is simply because it was too big to fit on any rocket made. So there was no other option. It wasn't something that was sort of done by choice. It was a sort of a forced design feature. So on the right-hand side of the screen, you can see the James Webb Space Telescope in its folded configuration. And in the middle, that's it when it's all unfolded. So you can see the sun shield has all been concertinaed in and folded upwards. And then you've also got the mirror flaps have been folded inwards. And you can see that that secondary mirror has also been pushed up above the telescope. It has the largest mirror that's ever been launched into space, 6.5 meters across. Of course, not one piece, it's all segmented. That sun shield is very important. We'll come back to that later, but it's got 5 unique layers. And then it's got 4 main instruments, and we will come on to those a little bit later. But if you have a look at the screen, that small gold picture, that is the fairing that houses all of the instruments, and that sits behind that gold mirror. Next slide, please. Okay, so if we're going to talk about the James Webb Space Telescope, we may as well begin at the beginning, and that is the sort of the origin, the concept of this telescope. And sort of work on Hubble's successor began before Hubble was even launched, and it began in 1989. So Hubble was launched in 1990. In 1989, there was a meeting designated the Next Generation Space Telescope Workshop, because astronomers recognized the need that, okay, you know, Hubble's launching imminently, but what's going to come next? What are we going to do after Hubble has been operating for 10, 20, dreaming of 30 years? And the initial concepts were twofold. So there was an idea for a 10-meter cooled telescope, so much bigger than the James Webb that we have today. And it would be placed on a high Earth orbit. So Hubble is in a low Earth orbit. It's a few hundred kilometers above the surface of the Earth. James Webb Space Telescope is much, much further away, beyond the orbit of the moon. We'll come on to the details later. But this 10-meter cooled telescope would be in a high Earth orbit, so between the Earth and the moon. The other idea was that actually we put a telescope on the moon. And because it's on the moon, we can make it even bigger and have a 16-meter telescope. And of course, at this time, you know, 16 meters is really exceeding anything that we even have on Earth. So, you know, it's sort of on that boundary of actually exceeding what we already had. So yeah, they were really some quite interesting concepts. And then, of course, we had Hubble launch and the disaster of Hubble's vision issues. And that really then spurred on the need for a successor, because all the astronomers were, oh my God, our telescope isn't working. We're going to have to replace it even quicker than we thought. So that was the first kind of real motivator for getting a successor for Hubble. And then, yeah, thankfully they managed to fix it, right? They fixed its vision issues. And then actually having Hubble as a successful mission inspired the astronomers even more to kind of get on and figure out what they were going to do next. So in 1996, a report was released sort of detailing what the follow-up for Hubble should be. And at that point, the ideas are kind of converged. And when they were like, 16 meters telescope on the moon, that is out the window. Put it out of your mind. We're not going to do that. 10 meters seemed excessive. And they kind of, you know, converged down to a telescope that was larger than Hubble. And we wanted it to be in the infrared to be able to see further back in time and have a bigger mirror so that we can still maintain sensitivity and also resolution. And the picture on the screen is actually one of the first concepts of the James Webb Space Telescope. And it's this really old, you can tell how old it is. It's like the really early computer generated graphics. But if you look at it, it's actually not that different to the telescope that we have. You know, you can see that there's some kind of enormous golden sun shield, and then you've got a segmented mirror, and then you've got a secondary mirror, which is kind of jutting out from that, redirecting the light of the universe. So even in the early days, you could say that the James Webb Space Telescope, it was taking on the form that we see today. Next slide, please. Next slide, please. Oh no. Oh no, we're okay. Right. So then we fast forward to 2000. And we have the 2000 decadal report. So every 10 years, astronomers all around the world, they submit their ideas and suggestions for what astronomy should be focusing on the next decade based on the successes of the previous one. And interestingly, in the 2020 decadal survey, we actually had the recommendations for the follow-up for the James Webb Space Telescope. So you can see how early, you know, astronomers have to think ahead. And in the 2000 decadal report, a successor to Hubble was named as high priority. And at that point, it was named the Next Generation Space Telescope and also Origins. The names are kind of intermixed. At that point, the telescope plan had grown again. So it was no longer a 4 meter. We were up to an 8 meter telescope. And this time it will be placed at Lagrange point 2. So this is far beyond the orbit of the moon. And we'll come to what Lagrange point 2 actually means a little bit later in the slides. It had a curiously low budget of $500 million, because it's significantly less than what was actually spent on Hubble in sort of today's money, and with an initial launch date of 2007. So yeah, let that sink in. 2007 was the original planned launch date of the James Webb Space Telescope. Bananas, isn't it? So anyway, in 2004, based on the recommendations of the 2000 Decadal report, construction began. In 2005, they realized, well, haven't we underestimated cost and time and the amount of technology that we need? And so the whole project was massively revised to a budget of $4.5 billion. So we can see that's a 9-fold increase in budget. The timeline was enormously extended. But at that point, they kind of thought, well, we think we've got the technology now that this new timeline and this new budget should be okay. We'll be able to stick with this one. And so instrument construction began all the way back in 2005. Next slide, please. By 2011, all of the mirror segments had been built. The construction of the sun shield began 2 years later. By 2016, all of the science instruments had been tested. The mirrors had all been put together. By 2019, the assembly was pretty much done. And then in 2020, we had final checks, including folding tests, and then 2021 launch, 14 years after that original planned launch date. So it's been a long time coming, this telescope, but it should be absolutely fantastic. Next slide, please. So a good exercise to try and understand the James Webb Space Telescope. Who was the main contractor? So even though it's a collaboration between NASA, ESA, and the Canadian Space Agency, it is by far mostly paid for by NASA and their various, sort of companies like Northrop Grumman and Goddard and all the other kind of ones that feed into NASA. And then the European Space Agency was, of course, responsible for the launch, and from that they said, we won't charge you for the launch, and in exchange our scientists get time on the telescope. So, and then the Canadian Space Agency provided sort of the least share of the funding, but they were still important. Okay, so no problem. So a good exercise for trying to understand the James Webb Space Telescope is actually compare it to Hubble, because it does have some similarities, but also a lot of differences. So on the face of it, Hubble and the James Webb Space Telescope, even though they look very, very different, they are actually very similar telescopes. They're both Cassegrain type telescopes. And what I mean by that is, normally I'd have a mouse and I would draw lines, but I can't do that. So you're going to have to picture it with your mind's eye. Is that the light enters through that dark tube of Hubble. It goes down to a mirror at the bottom, which is the primary mirror. It then comes back up to a secondary, and then that light is then pushed through a hole in the middle of the primary, right down to the back of the telescope where the instruments are. And you can kind of see this light path a lot easier on the James Webb Space Telescope. And if you look, you can see the primary mirror. That's the one that's collecting all of the light. So it's the hexagonal shape. Yeah, that's the one. The light is then focused onto the round thing at the end of those three arms. That's the secondary, which then directs the light into a tiny hole in the middle of that nose cone there to the instruments, which are hidden behind the mirror. So broadly, they are similar telescopes in the way that they collect the light and direct it to their instruments. Next slide, please. But a big difference with Hubble and JWST is the way that they look at the universe. So Hubble is primarily an optical telescope, or a visible light telescope. That is, it studies the universe with the same light that we can see with our eyes, which is, of course, a tiny, tiny part of the electromagnetic spectrum. So if you imagine the whole Earth, the whole of planet Earth, and the whole of planet Earth, you stretch the entire electromagnetic spectrum around planet Earth, and a wedge a mile wide, just a mile wide, is how much we can see of that electromagnetic spectrum. And so hopefully from that, you can understand that it's very important that we study the universe at all these other wavelengths, because the light that we can see with our eyes just makes up a tiny, tiny, tiny fraction of what is actually out there in the universe. So Hubble had a little bit of ultraviolet and infrared capability. So ultraviolet is shorter wavelength, higher energy, generally more energetic events, and it's light past the sort of blue-purple end of the visible spectrum. Infrared, on the other hand, is longer wavelength light. We're looking at cooler objects, less energetic events, and it's past the red end of the light spectrum. Now, the James Webb Space Telescope, as you can see in this picture, operates almost entirely in the infrared. It has a smidgen of optical capability right at the red end. It can see a tiny bit of what we can see, but it is very much an infrared space telescope. And it sort of overlaps with Spitzer. So it's sort of, you can think of it almost like a hybrid between Spitzer and Hubble, these two giants of kind of the previous generation of space telescopes. So it operates in what we call the near infrared, which is quite close to the red end of the spectrum, and then into the mid infrared, which is where it kind of overlaps with Spitzer. Next slide, please. So why infrared? Because, you know, we've mentioned infrared now quite a bit. We haven't really talked about why. And part of it is something called cosmological redshift. And what it enables is it enables the James Webb Space Telescope to physically see further back in time, because due to the finite speed of light, when we look out into the universe, because it takes light time to travel to actually reach us. So just as it takes time for you to walk from your house to the shop, it takes light physically time to move through the universe. It doesn't travel instantaneously. And so when we look out into the universe, when we see things which are more distant, we're actually seeing them further back in time as they were in the earlier history of the universe, because the light as it is now hasn't been able to reach us yet. And we live in a curious, expanding universe. And if we go to the next slide, there should be a lovely video. So if we can hit play. Yeah. Okay, so in this smoothly expanding universe, we're going to imagine, as our universe is expanding, it's moving everything further away from everything else. So the space in between objects is expanding. And if we just kind of keep playing this video, as an object's light is moving towards us, taking time to get to us, it's traveling through this expanding, stretching universe. And that stretches the wavelength of the light that's been emitted by, say, a distant galaxy, like in this animation. So although in the distant galaxy, the stars in it would have emitted their light in the ultraviolet or the optical part of the spectrum, as that light from the galaxy has been traveling through this stretching, expanding universe to get to us, its wavelength has got longer, and so the light would appear red, and then it would shift beyond the red into the infrared for the most distant stars and for those first galaxies, those first stars. And so there was a question and I only half read it. Is it in the chat? Does JJ see before the dark age set in or after? Oh, that's a really good question. So I believe the dark age of the universe refers to the time when the first stars hadn't quite formed. So if there's no stars formed, there's no starlight for it to detect. And so we're not expecting the James Webb Space Telescope to see the furthest back in time, because we've already done that. The furthest back in time that we can see has been with the Planck telescope and the cosmic microwave background radiation. And that's light emitted 300,000 years after the Big Bang. That's the earliest light in the universe. So the light that James Webb is going to detect is the light from the very first stars and galaxies that formed. So we're expecting 300,000 earlier. So we're expecting it to be 300,000 years after release, the formation of the universe, and a long time after that cosmic microwave background. Sorry, I got my numbers mixed up then. So yeah, the Dark Ages then is this period where gas is collapsing, the first stars getting ready to sort of start shining, but they haven't quite done it yet. And so when we get those first stars and those first galaxies, that's what the James Webb Space Telescope should be able to detect. We don't exactly know when in the history of the universe this happened, and that's one of the exciting results of this, is that it's going to tell us actually when those first stars formed, when they first started shining, and that is going to really help us understand star formation that we see today. Okay, so okay, good. Okay, so where are we? Yes, so expanding the universe, light is shining through, and it's, as this light's been traveling through this stretching universe to get to us, it's moved from that optical part of the spectrum, and then it's coming through, moving to longer wavelengths, down to the red end, and eventually into the infrared. So we've gone beyond the light that Hubble can see, and now we are down into the infrared, which is what the James Webb Space Telescope is going to see. And that's why we need it to be an infrared telescope, because that's where this light from the first stars is now. Okay, next slide, please. There we go. So this is just another example of another illustration of this stretching of the wavelength of light as this light from the first galaxies and the first stars 300 million years after the Big Bang has traveled through, stretched to get to Earth. Okay, carry on. Okay, and a really exciting thing is how different the universe is going to look when we've got these galaxies, a few hundred million years after the light from the CMB, few hundred million years after the formation of the universe. So this is a very famous picture. This is the Hubble Ultra Deep Field, where the Hubble Space Telescope stared at a seemingly, well, almost empty patch of sky. And if you look at this image, you can see sort of in the middle towards the bottom, there's a bright spot with some crosshairs in it, and that's a star. Every other point of light in this image is a distant galaxy. Every single one of them is just astonishing. And we've done some simulations, and we're going to see how this changes for the James Webb Space Telescope. So if we click and go to the next slide, there we go. This is the prediction for what it's going to look like for the James Webb Space Telescope. And you can see that we're seeing so many more galaxies. We're seeing a lot more sort of dynamic interactions. There's different colors going on. Obviously, this image is artificially colored because this light was being the infrared. So these are sort of artificial colors, but it's just going to completely transform how we look at the universe. Okay, next slide. So another reason why we want it to look in the infrared is the atmospheres of exoplanets. And there was another question about redshift, but I think we'll come back to it at the end, just because I'm wary of time, if that's okay. So, is the atmospheres of exoplanets. So most objects in space can be modeled as what's known as a black body. Now, a black body is a curious thing. It's defined as something which doesn't emit any more radiation than is incident upon it. So it absorbs sort of all the radiation that's incident upon it, and it stays at this sort of equilibrium temperature. It's not emitting more, it's not taking in more, so it's not heating up, and by not emitting more, it's not cooling down. And it just maintains a temperature. Many bodies are kind of modeled like this, so stars and planets and so on. The important take home for black bodies is that they emit light across the electromagnetic spectrum, but their peak wavelength, So the wavelength of light where they emit most of their light is entirely dependent on temperature. It doesn't matter a jot what they are made of. So it doesn't matter if it's a star, so it's hydrogen and helium. It doesn't matter if it's a rocky planet like Earth. It all depends on temperature. That's what the peak wavelength is. And there's a little graph here. And you can see, I haven't got my mouse. I just tried to move my mouse, but hopefully if you look at the diagram, you can see that we've got this sweeping line, and it's showing how the wavelength is going to longer numbers as we're looking at these curves for different temperature of bodies. So you can see for the 6,000 Kelvin body, that peak is right in the middle, the sun, you know, peaking in the visible. As we go to cooler and cooler objects, the energy is dropping. Also, that peak wavelength is shifting. And if we click, we can see this in a really visceral way if you've ever seen metal be heated. So you know that you start off with metal, you can't see it glowing because your eyes can't see it in the infrared. But as you start to heat it, it goes red, which is at longer wavelengths if we look at the graph. You then heat it more and it'll start glowing orangey, yellowy, and we can see this is moving through the visible spectrum to shorter wavelengths. And eventually you'll get to white hot, and this is where we've got a mixture of all colors, so we're sort of peaking similar to the sun. And for exoplanets, or even people, which are really cool, if we click, we can follow this trend. As the temperature decreases, we keep shifting to longer wavelengths. And for bodies, rocky planets, like the Earth, we want them to be like the Earth because that's the only sort of life we know how to find, then we see that the peak is right into the infrared part of the spectrum. So you can see on this black plot on the left-hand side, there's a very thin slither of a rainbow, and that's the visible range. And so you can see for exoplanets, we are deep into the infrared, exactly where the James Webb Space Telescope can see. So if we click again, one of the systems in particular that this telescope is going to be having a look at is the TRAPPIST-1 system, which is about 40 light years away. And it's a very exciting system of 7 roughly Earth-sized rocky planets orbiting a red dwarf star. And on the left-hand side, you can see the scale of the TRAPPIST-1 system compared to Earth. So their orbits are much inside the orbit of Mercury. They whip around their home star in a matter of days, very quickly. But their temperatures, so Earth was at about 300 Kelvin, and you can see how their temperatures, if we look at the right-hand plot, and you can see the colors in the on the key on the right-hand side, you can see how the temperatures of these planets are somewhat akin to Earth, and so that means we are peaking in that infrared exactly where the James Webb Space Telescope can see. Okay, next slide, please. Another reason why we want to have a look in the infrared with the James Webb Space Telescope is to peer through clouds of gas and dust. So yeah, of course I'm mentioning dust. And Dr. Dust wouldn't be a talk by me if I didn't bring up dust at some point, right? So with invisible, with the light that we can see with our eyes, we see all of this, what I think is beautiful cosmic dust, but most astronomers get very irked by it because they're like, oh, it's in the way, it's blocking my pictures, I can't see it. But when we switch to the infrared, it depends on which part of the infrared we're looking at, but particularly for the James Webb Space Telescope, where we're near infrared and mid-infrared, we're largely peering through this cosmic dust, and we can see what's hidden beneath it. So this is the Monkey Head Nebula, and on the left you can see what we see with our eyes, and then this is what it looks like in the infrared, and you can see that all of these newborn stars have suddenly been revealed that are hidden by this cosmic gas and dust. And it really gives us more information to help us understand stellar lives, because we're able to see parts of the stellar evolutionary tracts that we couldn't see before. And so, you know, peering in the infrared at these different objects, it gives us a really more complete picture. Next slide. So again, these are the very famous pillars of creation in the Eagle Nebula. So the wide field picture of the Eagle Nebula is there on the left. And if you peer in the middle, down, that's it. That's where the pillar, that's it right there, where the arrow was, just beneath the kind of dip. Yeah, that's where the very good, Tracy. Thank you, because it's just, yes, very well done. So that's where these fingers, these pillars of creation are. We can see in the visible, they are these beautiful towers of cosmic gas and dust going on. They are actively forming stars and, of course, planets. But when we look in the infrared, we peer through all of this gas and dust, and we can reveal, countless almost newborn stars that have been, hidden behind all of this amazing interstellar medium. So this is another thing that we want to have a look at with the James Webb Space Telescope. So if we click again. And this is my favorite fact about cosmic dust. Now, cosmic dust, it forms from the deaths of stars. It forms from the death of small stars like the sun, when they gently puff off their outer layers as they swell, as they age, and it cools and condenses, and heavy metals that they've produced during their life get turned into cosmic dust. They're also formed during the lives and deaths of the most massive stars. So in supernova explosions, they are really, really good at producing all of the heavy elements of the periodic table, so particularly those beyond iron, for example. And this cosmic dust, it permeates all of the interstellar medium. It's like smoke. It's these tiny, tiny solid grains. And by mass, cosmic dust is nothing in a galaxy. It's 10% of the interstellar medium, which itself is 10% of the mass of the galaxy. And yet, half of the starlight ever emitted in the universe has been absorbed by dust and re-radiated in the infrared. So by not looking at the infrared universe, we are literally missing out on half of the starlight that's ever been emitted. And it's really useful for tracing gas in galaxies. So this is a constellation which I'm sure is familiar to many of you. It's the Orion constellation. It's nice and high in the south of the minute, if you get a chance to have a look later, if it's clear where you are. And this is what we see with our eyes. You can see 3 stars in a line in the belt, and of course the sword with the famous Orion Nebula, and Betelgeuse, which Tracy has just pointed to, which gave us a bit of a wobbly a couple of years ago, right? But if we click, we can see what it looks like in the infrared, and you can see how this starry backdrop is just suddenly transformed into all of this tumultuous gas and dust. I mean, we're seeing the dust, which is therefore tracing the gas, because the two are entwined and mixed up. So it is really important that we look at this infrared universe. Okay, next slide. So we've looked at the light. It's time to look at the thing that collects the light, and that is the mirror. Now, the James Webb Space Telescope has a much bigger mirror, but surprisingly, it actually has a similar resolution to Hubble. So that is, it can see a similar amount of detail to the Hubble Space Telescope. And for those who are interested, I've put the full equation up on the board, well, up on the slide, which explains the relationship between resolution, which is this theta symbol on the left-hand side of the equation, in units of arc seconds, and we'll come on to arc seconds in a moment, is 1.22, which just comes out of some derivation, times by the 206,265 is because we're working in arc seconds. But then the real key bit is this fraction at the end. It's wavelength over diameter. And what you need to take away from this equation, if you're not interested in the numbers, which is fine, is that your resolution, it goes with your wavelength that you're looking at, and then it goes inversely with your diameter of your mirror. So a bigger mirror will give you a smaller resolution. That's what you want. You want to be able to see smaller details. But a longer wavelength, so a bigger number on the top of that fraction, is going to increase your resolution. So you can't see finer details. You can only look at the bigger things. And although the James Webb Space Telescope has this bigger mirror, so it should give us smaller resolution, because it also looks at longer wavelengths, they kind of cancel each other out, and they end up giving us a similar resolution to Hubble. So you can see here, I've thrown some numbers up on the board. The actual resolution of Hubble is about 0.05 arc seconds. I'll come on to arc seconds in one moment. And the James Webb Space Telescope is about 0.1, so reasonably comparable. However, this is an order of magnitude improvement over Spitzer, which was that infrared telescope I mentioned at the beginning. So that is the real thing for the James Webb Space Telescope, is that although when we see the pictures, you're not going to see more detail than you see with Hubble, but you will see more detail in a completely different part of the electromagnetic spectrum. And that's what's going to be really, really cool about James Webb's pictures. Okay, next slide. So I promised I would explain arc seconds. So if you think about a clock face, so you have seconds and then you have minutes, and then you have hours. So in astronomy, because why would they make anything nice and easy? You have degrees, and then you have or you have radians. It depends how you're calculating. You have 60 arc seconds in a minute, and 60 arc minutes then in a degree or a radian, depending on whether you're working in whichever unit. And the moon, for reference, is about half a degree, so that's 30 arc minutes. And so 1 arc second is, you would have to take the moon, divide it into 30 chunks. So then you'd have 1 arc minute, and then you'd have to take one of those chunks and divide it into 60 again. That would give you 1 arc second. Another way to think about this is if you take a football and you put it at one end of 7 football pitches stacked end to end, and you stood at the other end of these 7 football pitches stood end to end, the football has an angular resolution of 1 arc second, sorry. So yeah, crazy, right? Next slide. Okay, so one big question about the mirror for the James Webb is why is it sort of segmented and folded and terribly complicated? We've established that it has to be folded so that it could fit on the launch vehicle, because we didn't have a rocket big enough to fit it unfolded. And a solid mirror would have been too heavy anyway, even if we had a rocket big enough. And so the compromise is to have a segmented mirror. And it's hexagonal because hexagons have what's known as high filling factor. So you get lots of coverage, the closest you can basically get to a circle without it being a circle. You've got minimal gaps around the edge. And of course, the shapes fit together nice and easy. And a high filling factor is really, really important for when you're focusing. You don't want any gaps in your mirror, because then this will introduce lots of artifacts into your image and make it all terribly complicated. If we click and go to the next slide. This is just a nice little picture, which really helps illustrate kind of the size of the James Webb Space Telescope compared to people. So you can see some people in their suits in the clean room, and you can see one of the wings has been folded on the James Webb Space Telescope. And yeah, it is an enormous beast. So if we click again. So the mirror itself is made up of 18 hexagonal segments, as you've seen in the pictures. And the joy of this is that we will never have that repeat of Hubble, where so Hubble's mishap when it was first launched was that the mirror was slightly deformed, and it meant that the pictures weren't in focus, and so they had to do a mission using the shuttle to essentially give it a pair of glasses and fix it. But we won't get that with the James Webb Space Telescope, and that is because every single hexagon can be tilted and tipped and moved in 6 different directions. So there are 6 arms on the back of each of these segments, which you can see in the diagram here. So this is a picture of the back of one of the segments, which is held onto a gold stand with a wooden plate on the bottom. And these are called actuators, and they can tip and tilt the mirror in each of those directions. There is a 7th one in the center, and that actually deforms the mirror so it can bend it slightly. And what this means is that we can really control the position of each of these segments and make sure that we absolutely get pin sharp focus. But of course, it has to be done slowly, it has to be done carefully, and these actuators move at the speed that a blade of grass grows at. Very, very slowly, and that is because we require absolute precision. The segments have to be aligned within 1/10,000th of the width of a human hair. Yeah, it's astonishing that they can achieve that. They can actually move each of these actuators in steps of 1/20,000th of the width of human hair. So yeah, it's some incredible engineering. So if we click and go to the next slide. So the mirrors themselves, although they look golden, the gold is only actually a very small part of the mirror. It's just a very thin layer, 700 atoms thick on the surface. They're actually mostly made of a material called beryllium. And beryllium was chosen because it is light, very important when you're launching anything into space. You want to keep that weight down as much as possible. It's extremely strong. It's also, it doesn't change shape as temperature changes. And of course, this was a really important factor because the telescope itself is constructed in a clean room on Earth. So it's constructed at room temperature, but its operating temperature is only a few tens of degrees above absolute zero. So it sort of has to hold its shape over maybe 250 degrees, you know, that change. So this is why beryllium was chosen. And what they would do is they would cut a hexagonal mirror blank like this. They would then carve out the back of it. So you can see how the back of this mirror has got like this, this hatch pattern going across it. And that's where they've carved out as much of the beryllium as possible so that the strength just comes from this hatch. It's a bit like when if you've ever 3D printed anything, you don't tend to 3D print it whole. You kind of take out as much stuff in the middle as you can. And that's exactly what they've done here. They then slice that blank in two, and then they have two of the mirror segments. So if we click again, and then to do the gold coating, they actually use something called vacuum vapor deposition. And that is where they take a segment, they place it into a vacuum chamber, and they then have some gold in this vacuum chamber, which they evaporate. And because it's in a vacuum chamber, that gold is then accelerated across the vacuum and it sticks to wherever it can, and it is the segment that it sticks to. So it's a really, really thin coating, as thin as possible for weight purposes. And also, you know, gold is expensive. But the total amount of gold on the James Webb Space Telescope is, I think, is 1 or 2 golf balls. It's, yeah, hardly anything at all. So if we go to the next slide. Okay, so where is the Hubble and where is the James Webb Space Telescope? So Hubble is a few hundred kilometers above the surface of the Earth, 570 or so. So it's in what we call low Earth orbit. Whereas the James Webb Space Telescope, because it's an infrared telescope, and so in the infrared, we're kind of seeing the heat of the universe. We need it to be away from heat sources. That's away from the heat source of the Earth and the moon. And we also need it to be able to block the sun out as well. And the best place to be able to block out all of these massive, massive heat sources, because if we remember, you know, the temperature of the exoplanets sees them peaking in the infrared. Well, guess what? Exoplanets are just planets around other stars. So's Earth. So Earth is also peaking right at where we want this telescope looking. So we can't have the telescope anywhere near Earth. So the L2 point is 1 million miles away. It's 4 times the distance between the Earth and the moon, as you can sort of see in this diagram. And this is like the nearest that I could get to scale. If you see all of the other ones, they are horrendous. At least this one shows that the James Webb Space Telescope is a lot further out than the moon. So if we click again. And it's at this point called L2, Lagrange point 2, which is kind of just been something I've been referring to up until now. Now, the Lagrange points are named after Italian mathematician and astronomer Joseph Louis Lagrange, because he developed the mathematical theory to describe them. And the Lagrange points, they emerge naturally between any 2 large bodies, and they are gravitationally stable points. So you see them between the sun and the Earth, but you also see them, for example, between the sun and Jupiter. So there are 5 Lagrange points. The first one is between the sun and the Earth, same. And at Lagrange point 1 is where we place a lot of our sun observation satellites. The L2 point is just outside of Earth's orbit, and this is where we place a lot of our sensitive deep space telescopes. So the James Webb Space Telescope is going there, but we've also had ones like Herschel and Planck. They've all been there too. Now, L3 is exactly opposite planet Earth's orbit on the sun. So like, you know, sometimes there's that conspiracy theory, is it Nibiru, the light orbits the sun exactly opposite to Earth on its orbit? Well, they're on about this Lagrange point 3, but you know, there's nothing there. But there's another one there as well. You then have another two, which are L4 and L5. And L4 and L5 make equilateral triangles with the planet, the star, and then themselves. So that's their position 60 degrees ahead and 60 degrees behind of your planet. Now, at L1, it's gravitationally stable because the sun is obviously exerting a gravitational influence on the body in one direction, but the Earth is pulling back on it as well. And this leads to a very curious and wonderful phenomenon where anything that you place at L1 takes the same amount of time to orbit the sun as the Earth does. And the same is true for all of the other Lagrange points. So at L2, where we're placing the James Webb Space Telescope, here you've obviously got the gravitational pull from the sun, but you also get an extra kick from Earth. And so even though it's orbiting further out, it actually takes the same amount of time. So the James Webb Space Telescope is co-orbiting the sun with Earth. And the same is true for the other gravitational points. It's all to do with combinations of gravitational pulls. And at L4 and L5 of Jupiter, that's where you find the Trojan asteroids. But L4 and L5 are very stable. L2, however, is only quasi-stable. It's not fully stable. So if we click. So if you place something at L2, exactly at L2, and nothing disturbs it, then it'll stay there. As long as nothing disturbs it, you'll need a gnat to fart and it'll move off that L2 point. And so what we do instead is when we have objects that are L2, we place them in what's known as a halo orbit. So they orbit perpendicular to the path around the sun with Earth. And because it is a quasi-stable point, it doesn't require much fuel for us to do this. And the other advantage of having this halo orbit is that if we were to place our satellite exactly at the L2 point, then our satellite is going to see frequent eclipses of the sun by Earth and also by the moon. And the James Webb Space Telescope is solar powered. So cutting off its supply of power all the time is going to lead to a very dead telescope very, very quickly. So you place it on this halo orbit, and this halo orbit is enormous. It's bigger than the orbit of the moon around the Earth. It takes 6 months to complete one loop. So this animation is a little bit misleading. But that's why we have it at L2, because it is quasi-stable, it requires a little energy. We keep it in this halo orbit so there aren't eclipses, but the sun, the Earth, and the moon, we can block out all of that infrared energy from that sun shield, because everything is going to be in the same place in the sky all the time. They're always in the same direction because we are further out on that orbit. So that's why it's out at L2. We can block out all of that infrared light so that we can detect the infrared light from the universe that we are actually interested in. So if we just click, we should have a little picture come up. Yeah. So those are the advantages of the L2 point. You know, you get, it's thermally isolated, so you're away from that infrared energy. It doesn't need much fuel to maintain an orbit there. We, of course, get unimpeded views of half of the night sky. And we can be in constant contact with a satellite that's placed there. But the disadvantages, of course, is that it's 1 million miles away. If something goes wrong, we can't fix it yet. Because NASA did announce shortly after the launch of the James Webb Space Telescope, because the launch was so spectacular, that they do have plans afoot now to possibly go and refuel it in the future. But this is just kind of murmurings. If you're wondering why there is a picture of a saddle up on the screen, that is because you can imagine the Lagrange point 2 like a saddle. So if you've ever placed a stone in the center of a saddle, it'll stay there, but you nudge that saddle just the tiniest amount, and that pebble is rolling straight off and going whichever way it wants. And so that's why we have it in this controlled halo orbit, just to keep it where we want it to be. Okay, next slide. Okay, so we know all about the James Webb Space Telescope now, so we can talk about the launch. It launched from ESA's spaceport in French Guiana in Kourou, using the Ariane 5 rocket, which is the most reliable and successful launch vehicle to date. It is being replaced, I believe, this year, possibly next year, with its successor, the Ariane 6. And it was launched from French Guiana. Being near the equator is advantageous because it actually gives you extra speed as you're launching. If you've ever wondered why we never launch anything from the UK, this is one of the reasons. So it'll be interesting as they're trying to grow the UK space agency. Okay, next slide. The launch that ESA did was quite literally perfection. In this graph you can see here, which I shamelessly stole from Twitter, in the second green column you can see various numbers, and these are the ideal numbers. And if you look at the first green column, these are the numbers for what the launch actually was, and you can see they are almost identical. The launch, it couldn't have gone any better. And because that launch was so perfect, it meant that the James Webb Space Telescope had to use the least amount of fuel to get to its final destination. And it does mean now that instead of an original planned 10-year lifespan, it has enough fuel possibly to be there for 20 years. We'll have a better idea once commissioning has finished. So that's June-ish. But yeah, could be really, really exciting. So next slide. So I'm going to go through just some of the major points of deployment now after launch. I'd love to go through them all, but time, unfortunately. So launch was successful. We had some minor corrections. We had deployment of the antenna and the solar panels and so on and so on. Then we get to day 3, where we have sun shield deployment. So as I mentioned before, because the James Webb Space Telescope is an infrared telescope, it's seeing the heat of the universe. So it has to be cooled down. And most of this is achieved using this 5-layered sun shield with just passive cooling. So there's no active sort of mechanics going on here. It's just the existence of this sun shield itself. And this sun shield is enormous. If you see just down in the bottom left-hand corner, there's a tiny little person in a white suit in this image. There they are. That's how big this sun shield is. It is about the size of a tennis court. It is massive. And it will passively cool the telescope down to minus 230 degrees C. So that's 40 Kelvin or 40 degrees above absolute zero. So we click to the next slide. It is made of a really brilliant material called Captain. And if you remember the pictures of the Apollo moon lander, and it's got like this gold foil over it, that is Captain. And the one on the James Webb Space Telescope is not gold, it's silver with the bottom layer looking slightly purple. The purple comes from silicon, but the silvery is because it's got aluminium sort of threaded through it. It's what we call doping. And these materials are used in combination with Captain because they have high heat resistance, so they themselves don't heat up much, stable across a wide range of temperatures. And if we click, yeah, and also, of course, you know, we're familiar with aluminium being really reflective, so it will reflect away that heat, that infrared light. And also silicon has what's called high emissivity, so it really hates being warm. It's really efficient at getting rid of that heat. And so the combination of Captain, aluminium, silicon makes for a very, very effective heat shield. It's essentially what the sun shield is. A heat shield would be a better way. And it's got 5 layers because it's using the vacuum that's between the layers to help encourage that infrared light to wiggle its way out. You may notice that the sun shield is kind of dipped slightly in the middle, and that's on purpose. That is to encourage the infrared light to go out towards the edges, rather than kind of stay in the middle. And if you've ever wondered why it's this weird kite shape, well, that is simply because the kite shape is the minimum amount of material required for the maximum amount of cooling, and it all boils down to weight again for launch. And of course, you know, the bigger your sun shield, the more likely it is that a tiny micrometeoroid is going to hit it. So yeah, it was all about making the sun shield as small as it could possibly be, without, you know, so that it could perform correctly. Okay, so if we click, oh yes, that was the other thing to mention about the sun shield, is it has these 5 layers, but the 5th layer is actually a bit of a redundancy. So it's slightly thicker to protect against meteoroid tears, but it isn't really needed. So if over the course of the mission it does get little tears from micrometeoroids, it's fine, it's no problem. Okay, so if we go to the next slide. And of course, to protect against these micrometeoroids, they actually have stuck little seams along the sun shield. I think it's at approximately 2-meter intervals. They've kind of sealed the seams shut together. And so if you get a small tear, it's not going to rip right across the entire sun shield. It will stop at these various seams, and it'll help maintain most of the structural integrity of the sun shield. Okay, so we can go next. So one curious thing that was part of the sun shield's deployment, because it was many stages. First of all, we had the pallets come down, and then we had this thing. This should be a video, I'm hoping. If you, yes, good. Okay. Then we had this thing called the momentum flap deploy a few days into the process of deploying the sun shield. And everyone was like, oh, what's that? Even I was like, oh, what's that? That's curious. But the sun shield, being the size of a tennis court, is, of course, enormous. And so it actually acts like a sail with the solar winds. So these are the particles which are continually streaming from the sun. And these particles, just like wind on Earth, they would hit the sun shield that's acting like a sail and impart sort of momentum, and it would provide thrust to the telescope. And the way that the sun shield is constructed is, and the telescope and that, it's such that the center of the force from the solar wind is not aligned with the center of mass of the craft. So they are offset, because the James Webb Space Telescope is not perfectly balanced in the middle. You know, you couldn't hold it in the middle. Excuse me, sorry, that's my cat. If you can hear meows in the background, I do apologise. I might just let her out because she's scratching at the door, and if I don't, she's just going to continue screaming. So I do apologise. Come on. Oh, the perils of doing talks remotely. So where were we? Yes, so the center of mass of the pressure of the solar wind is not aligned with the center of mass of the telescope. And so what that actually results in is you've got this force acting off center, and it would act to spin the craft. And of course, that makes it hard for the telescope to stay on target. So if we click and go to the next slide. Now we can, of course, deal with this spinning. We have the reaction wheels, and they will, you can kind of collect your excess angular momentum as you've been moving the craft around, store it in these reaction wheels, and then dump it out later on. But having to make all of these course corrections and storing all of this momentum into the reaction wheels requires fuel in order to sort of dump it all out again and maintain while you're acting against this force and such. And without the momentum flap, the engineers would actually have to do this momentum dumping up to twice a week, and it would just burn through the fuel in order to keep the telescope on track. So what the momentum flap does is it shifts that pressure point from the solar wind so that it is as close as possible aligned to the center of mass of the telescope. That means that that telescope isn't going to be spinning around as much because of the solar wind. We're not going to be building up all of this momentum. We don't have to dump it as often, and it saves fuel. So it is a tiny little part of the telescope, and yet it is absolutely vital to the proper functioning of the James Webb Space Telescope. Okay, we can go to the next slide now. So we've had the pallets come down. We've had the momentum flap deploy. We had to release over 100 pins in order to allow the booms to come out and pull the sun shield into position. And with those pins, that was a scary moment because they were mechanical, and there was very little redundancy built into these pins, and every single one of them had to work in order for this sun shield to deploy. And by pins, it literally was. There are tiny little holes all the way through the sun shield where these pins were holding it together when it was all rolled up. The engineers just made sure that, of course, the holes don't line up once it's pulled outwards. And then, of course, once it's pulled outwards, it has to be tensioned. So the actual span of the sun shield is approximately 2 meters. And so they sort of pulled each layer taut one by one until we get the sun shield fully deployed. So we can go to the next slide. Okay, so it took about a week, just under a week, to get the sun shield deployed, and the next step was that secondary mirror. So the primary mirror is collecting that light, but the secondary one is essential. It is the one that gets the light to the instruments, and so it was stored in an upright position and extended like this. And the size of the secondary mirror is actually very similar to the primary mirror of Spitzer, so that previous generation infrared telescope. Imagine that now we're at the point where the secondary mirrors on telescopes are the size of our old ones. It's absolute bananas. You can go to the next slide, please. And of course, once we've got the secondary done, then it's time to unfold those wings on the primary, and they were done carefully, one side at a time. And once these wings were put in place, it was then time to spend, 10 days really moving each of those mirror segments from their stowed state into their deployed state. And it was great while this was happening. You could go on the website and they were showing you how each of the different segments was progressing. So you can see in that image how, some of them have raised, so far a few millimeters, some of them haven't moved at all. And it was really fascinating to track that. But all of them worked, they all moved, they got into their deployed state, which was the rough idea for focus for the telescope. So we can go to the next slide. And one question that I was asked while all of this was going on, I thought it was really good to put this in, was someone asked me, why didn't they put any cameras on the James Webb Space Telescope? Because obviously it would have been absolutely fantastic to watch all of this unfold. But it's twofold, really, the reasons why. So it would be very difficult to get cameras that will see the light that we see with our eyes. Very difficult to get them to operate at the temperatures of James Webb Space Telescope. So you remember that as soon as this sun shield is deployed, it is passively cooling that telescope. It's reflecting away all of the infrared light, and it's cooling it down to minus 230 degrees Celsius. And cameras just do not like that sort of temperature, not the ones that we're familiar with. And in order to get cameras that would work at these really cold temperatures, it would have required so much innovation and funding and time and effort that the payoff wasn't worth it, because the engineers actually get all of the data that they need from telemetry. So this is the information that the telescope sends back, through the antenna. So, it's got all sorts of gizmos and gadgets on it, which are telling them about the temperature of things and if commands are executing and the orientation of the telescope and so on and so forth. And again, the second reason is any extra cameras, anything electrical generates its own heat. And so then that's more heat that somehow is going to have to be radiated away when these cameras are probably on the wrong side of the sun shield for that to happen. So frankly, it would have just been a hot mess. And that is why they didn't put any cameras on there to watch this unfold. I thought I'd seen a selfie. Yes, so that selfie, I believe, was the reflection in the secondary mirror because it wasn't focused at that point. So where it was all off focus, they could kind of use the diffuse starlight to get an image from the secondary. So I believe that's what the yeah, it's not actually any camera. It's just the sort of out of focus picture on the secondary. But good question. Next slide, please. So we know that the James Webb Space Telescope fully successfully deployed, and we are now in what's called the commissioning phase, and it's a long old haul. It's 5 to 6 months of commissioning, and that is getting the telescope ready to do science. That's all commissioning is. So it's aligning the mirror segments, aligning the secondary mirror, making sure everything is working, testing all of the instruments, focusing, and so on. It's going to take 3 to 4 months for the telescope to actually cool down to its operating temperatures. So even though NearCam is being used at the minute in order to focus the telescope, it's still not going to be properly cool for a long time. And then, of course, MIRI, which is the mid-infrared instrument, because it's looking at longer wavelength objects, that means it's looking at cooler things. It needs to be cooled down to lower temperatures again, and it is done using liquid helium in a very innovative closed cryogenic circuit. So that can't be turned on until the telescope has cooled down to that minus 230, and then that liquid helium gets MIRI over the final furlong to where it needs to be to operate. So if we go to the next slide. What we do know is that the telescope has seen first light, as it were, because it has detected its first photons. To focus, it's been using a star in the constellation of Ursa Major, which is the bigger constellation of which the Plough or the Big Dipper asterism is a small part of. And the very exciting thing is that this star is a binocular target. It's about Mag 7, so it's not naked eye visible, but it's definitely visible in binoculars. And I've just put a couple of star maps up if you wanted to go and take a look at it, just because it's just something fun to do. You can look at what James Webb's looking at and just know that you're kind of staring at the same object. Should I? Yeah, you should use SkyGuide for that. In fact, these are screen grabs from SkyGuide available to download on the App Store for free. There we go. There's my advertising officially done for the day. But we can go to the next slide now. So the first job when it was looking at this star was to approximately focus each of the mirror segments. So in the GIF on the left-hand side, you can see how each of the mirror segments at the minute is producing its own image. And the one where everything is kind of fuzzy and blurred, that was the first image after they'd arranged the mirrors into the correct order. They then kind of got them as pin sharp as they could. And then what they do is they take each of those little pictures of the same star and they add them up into what's called stacking. So they just add up all of those photos of the star together, and then they get what is on the right. And so now what they're doing is the fine focusing. So if we go to the next slide, and this should be a little video. So in this video, you can see originally, the star would have been all over the shop. They then get into the hexagonal arrangement. They then put all of the star ones together into prime focus. And then what they want to do is look at this light from the star and get it as pin sharp as possible. So that's what you can see in the animation here. They will tweak the focus until it is an absolute point of light, as sharp as they can possibly get it. So that's what they're doing now, and that is going to take months of effort because it's doing an exposure, getting the data, having a look at it, move the mirror segment slightly, do another exposure, get the data, and on and on and on and on. So if we click to the next slide, and it's doing this with NearCam. But NearCam is not the only instrument on board. So The one that will take over and do all of the guiding and keeping the telescope on track is the fine guidance sensor / near infrared imager and slitless spectrograph, which is a massive mouthful. But this is the one which will point to a star field using the same catalogue of stars that Hubble does, just slightly updated. It will lock onto the bright ones and it will stay on track with those, and that's how it guides the telescope. So it will do an exposure, we'll keep doing exposures, monitor where those stars are in these exposures and keep them on those pixels exactly where they should be. And it works in conjunction with the gyroscopes and the reaction wheels and all the other gadgets on board which control the motion of the telescope. This instrument, although it is primarily used for guiding, it can do a little bit of science. So particularly for exoplanet science, if there are exoplanets around bright stars, which this camera can detect, then it can do some spectroscopy with that, or it can just take some images and we can get some transits, for example, where we see dips in the star's light from planets passing in front and so on. So, it can do a little bit. It's not the main science camera, but, if you're looking at something and it's got a planet around it, why not take some data and use it for science? So if we click the slide. So NearCam is the one that's being used to focus, and NearCam is the near infrared camera. It is the primary imager of the James Webb Space Telescope. So it is going to be the workhorse in terms of taking photographs. And it operates in the near infrared, so a tiny little bit of the red end of the spectrum, down to about 5 microns. And this one is passively cooled through the sun shields, I've mentioned before. And what's really interesting about NearCam is it actually can do something fantastic, something we've not been able to do before. And that is it can stare at 2 patches of sky simultaneously and 2 wavelengths at the same time. So in the picture, you've got the 2 different fields of view of NearCam, which is just 2 patches of nearby sky bounded by the red box. But the red boxes are 1 wavelength, the slightly longer wavelength, and then the little blue boxes are then the shorter wavelength. So having instantaneous imaging in 2 different wavelengths of 2 different patches of sky is absolutely phenomenal for astronomers, because normally, when you're taking data at different wavelengths, you have to use one filter, switch over to the next, and so on. Whereas this, you can get it at the same time. It's going to be really interesting for detecting unusual transients, so changing phenomena. So we can go on to the next slide, please. So NearCam is equipped with all sorts of tools and tricks. So one thing that it's equipped with is something called a coronagraph. Now, coronagraphs are, you can imagine if you've got your camera and say you're looking at a bright star, and that bright star is, of course, completely flooding the entire image. Well, if you can just kind of have a little mask to block out that bright star, then suddenly you can see everything that's around it. It's like if you've ever tried to be go out stargazing and there's a bloody lamppost in the way. And so what you'll do is you'll stick your hand over that lamppost and then you can see more stars. And it's exactly the same effect here. And this is, I forget which star it is now, but this is a wonderful real animation taken over about 5 years, I believe. And what they've done is they've used a coronagraph to block out the light of the central star. And those little dots that you can see going around those stars are actually planets. These are actual photos of actual planets moving around a distant star. And this is the sort of reason why you might use a coronagraph, is so that you can block out the starlight and detect the light from the much, much fainter planets going around them. So NearCam has some spectroscopic capabilities. So that is, it can split light into its constituent wavelengths. And we'll come on to spectroscopy in a little bit, but primarily it's for taking pictures. And if we click and go to the next slide, it has dozens of filters. It's got 48 elements in total, including the coronagraphs. So it can do wideband imaging. This is where it's looking at lots of wavelengths of light simultaneously, or it can do very narrow band imaging where you're looking at one particular wavelength of light because you're searching for something specific. So it's a really, really flexible tool. It's got lots and lots of different variability. Okay, so if we go to the next slide, we come on to NearSpec, which is the near-infrared spectrograph. Huzzah, for once, astronomers have named things properly and easily and straightforwardly. So just like near-cam is the imager, near-spec is the spectrometer, the spectrograph. It operates at a similar wavelength range to near-cam, but this one will split light up into its constituent wavelengths. So just like when sunlight shines through a raindrop and then we get a rainbow, that white light is being split into all of its constituent colours. It's exactly the same thing with a spectrograph, but it just does it at a much, much finer resolution. So you can see lots more detail, lots more wavelengths. You either get emission or absorption spectrum. So emission spectrum is when you're looking at the light that's emanating from an object, and it will emit light at specific wavelengths depending on its composition. Whereas with absorption spectrum, you've got maybe some kind of gas cloud in front of the star, and that material in the gas cloud will absorb light at very, very specific wavelengths. It will take it away from that starlight, and so then you get black lines. So you can see an example of an emission spectrum and an absorption spectrum at the bottom. And this is a really, really powerful tool for understanding the atmospheres of exoplanets. So this is the tool. If you want to figure out what's going on in the air of alien worlds, this is your guide. So if we click and go to the next slide. So what will happen is to the left of this picture, there is a star which has emitted some light, and it is just passing through the atmosphere of an exoplanet. And we can imagine our detector is on the right-hand side. So James Webb is over on the right-hand side. And if we look at the top left bubble, you can see that this starlight has, every single color of the rainbow consisting within it. As that light passes through that atmosphere and it emerges on the other side, the elements in that atmosphere, they have absorbed some of that starlight at very, very specific wavelengths. And by looking at which wavelengths are now missing, so these dark lines, this absence of light at very specific wavelengths, we can figure out what's going on, because every single molecule, element, chemical in the universe has a unique fingerprint when it comes to spectroscopy. Everything absorbs light at very specific frequencies, and no two are the same. These are the chemical fingerprints that you might have heard mentioned. By looking at all the different elements, seeing what light is missing, we can determine what is in the atmospheres of these exoplanets. Is it carbon dioxide? Is it water? Is it more exciting things like methane, elements that, constantly need replenishing by, something, if you get my drift. So yeah, near-spec is your one if you're interested in planet atmospheres. So we're going to go to the next slide, please. And another useful thing with spectroscopy is not just exoplanet atmospheres, but this is what we can use to figure out how far objects are away. This is where we're using something called relativistic redshift to figure out distance. And if you are interested in the equation is up on the slide, but we can, as we learned in the beginning with redshift, where that light is passing through and expanding the universe, and so the wavelength of the light gets stretched, it moves to longer wavelengths, moves into the infrared and such. Those emission lines that or absorption lines that we're looking for will still exist, and they'll always be separated by ratios of the same amount. They will kind of shift together in space. They will shift together in wavelength. And so we can look at, for example, hydrogen maybe in the lab, have a look at its emission or absorption lines. And then we can look at a galaxy and we can identify these lines, and we can think, well, I know this galaxy's got two lines close together at longer wavelengths, and then one at sort of middling wavelengths, and then one at really short wavelengths. And I know that that pattern is hydrogen, but it's not at the right wavelengths. And that tells me that this galaxy is at a reasonable distance away from us. And that shifting is how we figure out redshift. So it's the observed wavelengths of light compared to the emitted wavelengths of light in the equation on the slide. And of course, the further away your galaxy, the further into the red end of the spectrum or the infrared, that these lines are going to be shifted. So yeah, spectroscopy is a really powerful tool. So if we go to the next slide. So NearSpec is not just a simple spectrometer splitting up light like a rainbow. It has something which is really powerful. It's a kind of a new technology that's come into astronomy in the past decade, and it's called integral field unit spectroscopy. And what it means is we take a photo, so this is a photo of a galaxy, and then instead of just having a pretty picture, each pixel in that picture holds a spectrum. So it's like taking a deep dive into every single pixel. And in each pixel, we know what that part of the galaxy is made of. And it is really exciting to be able to figure out how trends change across disks of galaxies and so on. So yeah, this is a brand new, exciting, very interesting tool. But can you imagine that every time you took a picture of the night sky, you could dive into each of those pixels and it would tell you how much gas there was, what that gas was made of, if it was hot, cold. Yeah, that's what integral field unit spectroscopy does for us. Very, very cool. So you can go to the next slide, please. It also can do something called multi-object spectroscopy. So it can take lots and lots of spectra, not just of one object, but over a very large area. So you can isolate, for example, particular stars in a star field, or if you're looking at a cloud of gas or a nebula, for example, you can focus in on particular filaments. Or maybe you want to block out the light from very bright nearby stars. You only want to take spectroscopy of a very small region. And if we click, and we go to the next slide, this is the field of view of NearSpec's multi-object spectroscopy tool. And each quadrant, so each of those squares, has 250,000 microshutters. Each of these microshutters is about the width of a human hair, and they can each be individually controlled using magnetic fields. And so you can just isolate a really tiny part of a galaxy or a tiny part of a gas cloud and just get the data from that, block out any annoying starlight or such like. And it is such a fascinating development. It's a brand new tool. Nothing else has anything like this. And it's going to be really, really exciting. So we can go to the next slide, please. The final instrument to mention is MIRI. So this is the mid-infrared instrument, and it is a bit of a workhorse. It does imaging. It also does spectroscopy, but it's in the mid-infrared. So it's looking at longer wavelengths, and it too has coronagraphs. It has a mix of filters, and this is the one that has to be cooled further using that liquid helium. So you can see in this picture, this is the field of view of MIRI. And different parts of that field of view can do different things. So you can, take images for most of it. There's 3 different coronagraphs looking at different wavelengths, so on a different section. And then you've got spectroscopy and so on. So if we go to the next slide, one of the most exciting things about James Webb's imaging system is that you can use more than one of these instruments at once. And that is pioneering. Holy moly, it is so exciting. So it doesn't have to be part of the same project. It could be just projects, individual projects that happen to be looking at nearby patches of sky, and you can run those projects at the same time. So this means just so much more science is going to get done. So you can do all different combinations. This is the field of view of the James Webb Space Telescope, and you can see that each instrument is looking at a slightly different patch of nearby sky. So you can have NearCam operating with MIRI, or you want NearCam and NearSpec operating. They won't be looking at the same objects, but they'll be looking at nearby fields of the sky, and being able to just employ them at the same time is, revolutionary. Okay, next slide. Okay, so we have finished instruments, and we have done the James Webb Space Telescope sort of as a whole. And we are on to the final part, which is science. So it is going to touch on basically every single branch of astrophysics that you can possibly think of. Solar system, newly formed stars, exoplanet atmospheres, galaxies, nearby, distant. It's going to look at the cosmic web by studying the structure of and the relationship between galaxies. It's going to investigate dark matter and dark energy, and of course supernovae, even the electromagnetic counterparts to gravitational waves. It is going to just revolutionize astronomy in ways that we can't even imagine. That's going to be the best bit. We can plan all of this science, but it is going to chuck some kamikaze crazy things out in the universe at us, and that's going to be the best thing. So if we click the slide, a big question is choosing projects, right? How do you decide who gets to use the telescope? Now, in the early days of astronomy, back in, ye olde days of 1800s, it was whoever built the telescope and whoever gave them the money to build the telescope, that was who was allowed to use the telescope. That's why you had all of these crazy, men in wigs and crazy ideas building their own telescope because no one else is going to let them use theirs, so they had to make their own. But of course, today, telescopes are not built by one man and his miserable wife or whoever he's corralled into doing it. The cost is too much. It's too varied for simply one person. The expertise required to build modern telescope, it transcends countries, continents. It's global efforts these days. And so it does lead to an enormous problem when you've got all of these people involved in designing and building the telescope. Who gets to use it? Because there's only so many hours in a year. So if we click the slide. So the first year of observations are known as cycle 1. And the second year will be cycle 2, and so on and so on. And they're divided into sort of 4 project areas. So first of all, you have what's called the calibration programs. These are there to test the instruments, establish baselines, so find if there's any bad pixels, if something's not responding correctly, and so on. They'll look at kind of standard objects that we already understand, so that it'll help us characterize the imaging system. They're also there to, test the tracking capabilities and so on. These programs are done by the people who built the telescope, people who built the instruments. But of course, these are not really science. So they also get guaranteed time observations. So we click the slide. Guaranteed time observations in the first year amount to almost 4,000 hours. And these are the people who built the telescope. They have to do all the grunt work with making sure it's working properly. So of course, it's only right that they get to do some science too. And there are 2 programs, and this is very exciting, are going to stare at the Hubble Ultra Deep Field, but using the James Webb Space Telescope. So that simulated picture that I showed you right at the beginning is going to become real life. It's going to discover new galaxies with amazing active black holes and also allow us to study known galaxies in a lot more detail. If you were wondering where the Hubble Ultra Deep Field is, it's in the constellation of Fornax. It's that circle, but obviously much smaller than that circle, but that's where it is. So we can go to the next slide. Oh, and this is just a revised picture again of the one that I sort of showed you in the beginning, but a bit bigger. So there's lots of exoplanet projects in the guaranteed time. As I mentioned at the beginning, looking at the TRAPPIST system, but we're also going to be looking at worlds in our solar system. So we're going to be having a look at Europa, which is a moon of Jupiter, and Enceladus, a moon of Saturn. And in particular, we're looking for signs of submerged hydrothermal vents with the James Webb Space Telescope. So yeah, it's not just things far out in our galaxy. It's going to be studying things very nearby. So we can click to the next slide. So another set of observations that we have, the third set of observations, are the Director's Discretionary Early Release Science. So it's a small amount of time, 500 hours, and these are high priority exploratory projects. It's to see how the telescope performs with different types of objects, with nebulae, with galaxies, with nearby galaxies, distant galaxies, star-forming regions, the solar system. Because of course, these are all different brightnesses, they all require different filters, and so on. It's also to help develop the image processing systems, because it would be amazing if the images came down from the telescope like they do on the right, but actually they'll come down like something on the left, where you'll have multiple exposures of different parts of the image using different filters. You might have satellites, well, not for JWST, but in, other images, you'll have satellites you've got to get removed. For JWST, there'll be things like cosmic rays, which you have to get rid of. All sorts. And so, a lot of effort has to go in to make a pretty picture. And, you know, it's really to put the telescope through its paces. That's what those 500 hours are all about. So if we go to the next slide. But by far the biggest chunk of science belongs to the General Observer Programme, 6,000 hours in total. And these are projects proposed by the worldwide astronomical community, people who weren't involved with building the James Webb Space Telescope, but find its capabilities uniquely placed to help their scientific endeavours. And for the James Webb Space Telescope, these proposals were selected by a process called peer review in a dual anonymous process, where genders and names are all hidden. And this is really, really important because it's shown, there's been tests done with the Hubble Space Telescope, that as soon as you introduce double-blind peer review, when the reviewers don't know who the people are and the people don't know who the reviewers are, suddenly, if you look at the graph on the right, the number of proposals by people who have never won time on a telescope before, they shoot through the roof. They go up to a 30 to 35% share of brand new astronomers getting to use a telescope based solely on the merit of the science that they're proposing, not because of the name that they hold or don't hold, as it were. And then if we have a look at the graph on the left, you can see where at cycle 26, because that's the latest data that I could find, at cycle 26 for the Hubble Space Telescope, where dual anonymous processes were introduced, you can see that actually the proposals that were going to men and women was pretty much equal, whereas prior to that, when there were genders and names assigned to proposals, women were not selected, and it goes to show that there was no real good reason for that other than internal biases. So that's the dual anonymous process, and it is really important for encouraging diversity in astronomy. So if we go to the next slide, competition for the first year of science on the James Webb Space Telescope was really fierce. A success rate of 20 to 25%, depending on how many hours your project took up. So yeah, 1 in 4 or 1 in 5 chance of being successful. And this is before the telescope even flew, before we even knew if it would work. So this is only going to get worse as time goes on. So if we go to the next slide. So lots of projects to do with characterizing the atmospheres of rocky planets, particularly around small red dwarf stars. These stars flare a lot, so one question to address is, do these flares impact the habitability of orbiting exoplanets? If we go to the next slide. Over 10% of the General Observer time is being lent to the Cosmos Webb project, which I like because this is the field that I studied during my PhD, and it's to extend the multi-wavelength nature of the Cosmos survey, peer deeper, find new galaxies, thousands of new galaxies, these brand new ones, right at the start of the universe, the first galaxies. And then also study known galaxies in more detail, because there's 500,000 galaxies in this patch of sky. And yes, compared to the full moon there, just to sort of give an idea of scale. And we're going to be able to understand these in even more detail. So yeah, very, very exciting. Next slide, please. If you remember, a few years ago, we had that very dramatic photograph of a shadow of around the black hole in the center of galaxy M87. They're going to use the James Webb Space Telescope in partner with other telescopes on Earth to try and image this black hole at the center of our galaxy. So hopefully we're going to get something like this, but for the Milky Way. So if we go on to the next slide. We're hoping to study new stars that have recently formed in neighbor galaxy M33, which is a triangulum galaxy. We're going to be studying all of the planets beyond Earth and a lot of their moons as well. Asteroids, comets, interstellar interlopers like Borisov and so on, all targets. So if we go on to the next slide. And so hopefully that kind of just gives a flavour of all of the science that the James Webb Space Telescope is going to achieve in its first year. First image, not until June-ish. And remember, the detail level will be similar to what we can get with Hubble, but of course, in the infrared, an entirely different part of the spectrum. And it's not going to be an imaging telescope, unlike Hubble. Most of its time is going to be spent doing that spectroscopy, really investigating the composition of objects and also things like their distances. But by far the most exciting part of the James Webb Space Telescope is what we can't plan for, because yeah, it is going to blow our tiny little minds away. Can't wait. So if we click the next slide. That is the end of the talk, and I know it's been a long one, and I tried to cut this down as much as possible, but I hope that I've managed to do the James Webb Space Telescope justice. And of course, I'm really sorry about all of those delays at the start of the talk. But yeah, that is everything that you could possibly need to know, I think, for the James Webb Space Telescope.